All right, so for this next chapter, we're going to go over section 5.2, the first derivative test. Now, I haven't even finished recording the video, but I already know that this is going to be one of the longer ones. And seeing how there's a lot of steps involved with these types of problems, I'm just going to go ahead and make the problem set due Sunday night. That way you have plenty of time to really take your time with these problems and make sure that you do them. And I'm also going to try my best to start working out the solutions to the problem set as opposed to just giving you the answers, because these are things that, because since there's so many steps, I just want to make sure that you guys get this correct. So let's just kind of go ahead and get started. So from the previous section, we were already talking about how to find the critical points of a graph, right? So, and really even finding the critical points given a function. So if we just kind of look at this graph, what you'll notice is we have critical points right here because we have a relative maximum there, and that's actually the absolute max. And then over here we have another critical point because, you know, that's where the horizontal lines are 0. All right. Here we have another critical point because we do have a relative maximum there, but it doesn't really have a horizontal asymptote. But still, we can just figure out that that's the critical point. And that's essentially it. So again, notice here that you have your slopes or horizontal tangent lines where the slopes are 0. And essentially what we're going to do is, most of the time the curve is not going to be given to you. A lot of times they'll just give you the raw function and you have to kind of figure it out yourself. But what they want you to figure out how to do is determine whether or not the function is increasing or decreasing, and you're going to figure that out from looking at the slopes as you go between the critical points, right? So you'll notice if I look at this graph, if I were to draw the slope of a tangent line here, that's a positive slope, positive slope, positive slope, positive slope, until you eventually reach this slope of 0. And then what you're going to notice if I look at these slopes over here of this curve, right? Negative slope, negative slope, negative slope, negative slope, negative slope, negative slope, until you reach this horizontal slope right there. So you'll notice that between critical points, a lot of times the slopes are going to change from like positive to negative, or in this case from negative, and then these become positive. And you're going to use that to kind of understand what the behavior of the graph is. So what you'll notice is the critical points. If we look at the interval from negative infinity up until 3, so really from negative infinity to here, you'll notice that this function has positive slopes, right? Like all of your f prime of x, because remember, f prime represents the slope of the tangent line, right? So all of these slopes are pretty much positive from negative infinity to 3. When I look from 3 to 5, so from 3 to 5, all of these slopes right here are negative. You can just, I kind of drew them for you. So you have negative slopes right there. And then over here from 5 to 6, so from 5 to 6, you'll notice that this graph is pretty much increasing the whole time. So all of those slopes are positive. And then from 6 to infinity, like if I went from 6 and beyond, you'll notice that all of these slopes are pretty much negative. So the derivatives are negative. Right? And now that you know whether the slopes are positive or negative or whatever, that's going to tell you whether it's increasing or decreasing. In this case, increasing and decreasing. Okay? So again, a lot of times you're not going to be given the graph, and you have to determine from this whether or not you have a relative min or max. So, I mean, you can kind of just tell from the direction of these arrows that this is eventually going to lead into a maximum value there. This is eventually leading into, if you're going from negative to positive, to a minimum value. And this is eventually going to lead into, from a positive to a negative, you have a maximum value there. Okay? You're going to use this principle to pretty much answer almost all of these problems. All right? So, all right, let's just kind of get into it. So the first thing I kind of want us to do, and I don't know if the AP exam asked this as much anymore. They used to a lot more when we didn't have, you know, when graphing calculators weren't a requirement for the class. But I mean, who knows? Occasionally they might still, but I still think this is important for us to understand the behavior of what's going on. So as far as curve sketching is concerned, they say sketch the function f of x is equal to x cubed minus 3/2 x squared plus 2. So you notice we don't have a graph, And we pretty much, based off of our knowledge of increasing and decreasing intervals and maximums and minimums, we're going to go ahead and see what we can do to kind of sketch this graph as best as we can. So, in order to determine increasing, decreasing intervals and maximums and minimums, the one thing you always have to make sure you know how to do is, or the first thing you always do is figure out where the critical points are. So as far as critical points, you got to set the derivative equal to 0, right? I forgot to mention here my critical points were at x equals 3, 5, and 6. Well, whatever. I already talked about that. So let's go ahead and find what our critical points is for this. So obviously we're going to take the derivative. So f prime of x is equal to, that's 3x squared. All right, so yeah, the derivative is going to be 3x squared, and then when I take the derivative of this is going to become 2 times 3 halves is negative 3x, and then plus 0, well, we don't have to write that. So now what we're going to do is we're going to set this equal to 0. And if you remember from your good old Algebra 2 days when you had to like get a quadratic or solve quadratic equations, you're going to factor this side as much as possible, so you're going to get 3x parentheses x minus 1. And then you're going to determine your critical points from this. So when you set each of these equal to 0, you get x is equal to 0, and this becomes x equal to 1. So these right here are our critical points. Okay, so I'm going to use this table, and you're not going to have to write this table out every single time. Later on in the section, I'm going to show you kind of my way of doing things. I still have to double check with the AP community to see like what is the exact format that the AP exam is looking for to get the most points. But for right now, I'm just going to show you kind of what I was taught in college and what most professors would expect from you. So, all right, so we determined that these are the critical points. Okay, so I'm going to go ahead and I went ahead and made a nice little graphic organizer for you so that you can kind of see what we're doing. You don't have to do this every time, but I know I'm going to have a critical point from at 0 and 1. So really, we're going to be paying attention to the intervals from negative infinity to 0, from 0 to 1, and from 1 to infinity. Okay? And then what we're going to do, because again, what you want to do, like in between critical values, you want to kind of use a test point in between these two to kind of determine, because you'll notice like between these two critical values, aren't the slopes always going to be the same? So if you just kind of figure out what one of these slopes are, that'll tell you what the behavior of the graph is. All right, so let's kind of do it. So you're going to pick a test point in between this interval. So I think the easiest number to work with from negative infinity to 0 would be negative 1. You know, plugging 1 into a function is pretty simple enough. Probably the easiest number to use here would be 1/2. And then I'd say the easiest number to use here would probably say 2. Right? So then, again, what we want to figure out is we want to know what is the behavior of the slope. Because again, knowing the behavior of the slope, because if the slopes are positive, that's going to tell us if it's increasing or decreasing. If it's negative, it's going to tell us if it's decreasing. If it's positive, it's going to tell us that it's increasing. If it's negative, I don't even remember what I just said, but I don't know. Sorry about that. But so now what we're going to do, we're going to plug in these values, these 3 test points, into our derivative function. So I'm going to check f prime of negative 1. Well, that's going to be, let's see, if I put a negative 1 into this, that'll be negative 3 times negative 2. That's going to be 6, which is a positive value. So we know that f prime of negative 1 is equal to 6. We know that that's positive. So essentially that we can conclude that is increasing. All right. Then I'm going to plug in my my test value of 1/2. So f prime of 1/2, that's equal to, let's see, that's pretty much 1.5 times negative 0.5, which becomes negative 0.75. So I know that f prime of 1/2, or negative 3/4, is equal to negative, I'll just say 3/4. So that's a negative value, and that's telling us that it's decreasing from that interval. Right? All you have to do is pick one test point, and that'll tell you what all of the slopes are how all of the slopes are behaving from that interval. Then I'm going to use 2. I'm going to plug in my test value of 2 into my derivative. So f prime of 2 is equal to 6 times 2 minus 1 is 1, so that's positive 6. So f prime of 2 is equal to 6, that's a positive number, and that's telling us that it's increasing from that interval to that interval. All right, so if we wanted to kind of create a sketch of this, now, okay, yeah, and if we want to kind of create a sketch of this, well, we have to understand which one is a minimum, which one's a maximum, where it's increasing, where it's decreasing. So you'll notice here at 0, if it's increasing here and then decreasing there, that means that we have a maximum at 0. If I'm looking at 1, if I know that it's decreasing here but increasing there, that means that you're gonna have a minimum right there at 1. Anyways, so what we're gonna do is we're gonna go ahead and like see, okay, let's try it. First of all, let's figure out where these points are located at 0 and 1. So, because I mean, this is kind of important. We want to know where our max and mins are. So first, let me figure out where 0 is located. So f of 0 is, well, if I plug in 0 into all of that, I get 2. And if I plug in f of 1, I get, let's see, 1 minus 3 halves plus 2. That's pretty much going to be located at 3 halves, or like 1.5. So if I graphed 0, I know that my y-intercept is at 2. If I graphed point 1, at 1, it's at 1.5. All right? And then essentially I know that it's going to be increasing from negative infinity to 0. So it's going to be like increasing until we get to this point. Okay? And then it's going to be decreasing from this point to that point, right? And that, again, you'll see that created a relative maximum. And then we know that after this point, or after 1, it's going to be increasing again. And there you go. Again, this is not what the exact graph looks like, but it is a rough sketch, and it does tell you what the behavior of the graph pretty much looks like. Okay, so now let's kind of go into some regular application using velocity and acceleration. So it says here, a particle moves along the x-axis with the position function given below and describe its motion. So again, we have our position here, right? So if we want to know what the description of its motion is, we probably should figure out where the velocity is at. So we know that position is the original function, velocity would be our derivative. So the derivative of x, and I'm just going to say is equal to the velocity derivative of t of x of t is equal to the velocity of t. And then we're just going to go ahead and do, we have to do quotient rule for this one. So it's going to be t squared plus 1. So bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And so, okay, I'm going to make this look a little bit nicer. So then what I'm going to do is I'm going to have, let's see, 8t squared plus 8 minus 16t squared over t squared plus 1. And then when I go ahead and I combine like terms, I'm left with 8 minus 8t squared over t squared plus 1 squared. Sorry guys, I got interrupted, but now I'm back. So essentially what we want to do, now that we went ahead and took the derivative of this position function to get our velocity function, we want to figure out where this velocity is 0. So we're going to go ahead and set the numerator equal to 0 and the denominator equal to 0. And I mean, there's really no value in the denominator that would make the 0, because I mean, this is just always going to be a positive number, and something that's always positive plus 1 squared will never give you any value that works for this equation. So what we'll do is we'll just set the top equal to 0. So if I have 8 minus 8t squared is equal to 0, I add the at, divide by 8, so I'm left with t squared is equal to 1. When you square root both sides, you have t is equal to plus or minus 1. Now, I know that this problem, I mean, it doesn't make much sense for this problem to have a negative time, but just for the sake of understanding what's going on and, motion and all of that, let's just kind of keep it as plus or minus 1. I know it doesn't make sense in practice, but that's all right. We'll survive. So now what I'm going to do is I'm going to replicate this table, even though I'm not going to use this table as much in the future when I do other problems. But what I'm going to do is I'm going to go ahead and kind of understand what intervals I'm working with. So I'm working from the intervals with -1 and 1. So really from -infinity to -1, from -1 to +1, and then from 1 to infinity. Okay? So what I'm going to do is I'm going to pick test points within these intervals to kind of see what the behavior of the graph is. And the reason why we want to know what the behavior of the graph is because if you remember when we, like from, I forget which chapter it was, but I think it was 4.2, if we have a negative velocity or a negative derivative in our, a negative value for our derivative, then that's pretty much telling us that it's moving to the left. If you have a positive value for velocity, that's going to tell us that it's moving to the right. So I'm just going to kind of show that to you in an organized way. So the test point I'll use for this one will be like -2. For this one, I'll use 0. And then for this one, I'll use +2. And now with these test points, we're going to plug those into our f of x. And then from there, we're going to come up with our conclusion. All right, so let me make this into a nice little table. Hopefully my lines are straight. All right, so when I plug in -2 into our derivative function, right, or into our velocity function, I know that v of -2 is equal to, let's see, I'm probably going to plug it into this one. I think it's the nicest one to plug it into. So I'll do 8 minus 8 times 4, because 2 squared is 4, divided by 4 plus 1 squared, which gives us -24 over 25. So I know that f prime of x is going to be a negative value. So what this is telling me is that it's moving left. And then what I'm gonna go ahead and plug in 0. So v of 0 or x prime of 0. I'm gonna go ahead and say that that's going to be equal to 8 over 1 squared is just 8. So there we end up with a positive value. And that's telling us that it's and if our velocity is positive, then that means it's moving right. And then finally, when I plug in 2, I think I'm going to end up with the same thing because I'm plugging it into values that are squared. So v of 2 is going to be 8 minus 8 times 4 over 2 squared plus 1 is pretty much 5 squared, which is again -24 over 25. So we also have a negative value there, and this is telling us that it's moving left. Okay, so again, we could also use this idea of taking the derivative, setting it equal to 0, finding our critical points. We can use that to pretty much determine whether the object is moving left or whether it's moving right. And that's, you know, we're using our knowledge of the first derivative test. So let's just kind of grind through these next few problems. So if I were to do this one, use the first derivative test to find the relative extrema, well, to find the relative extrema, I got to understand where it's increasing then decreasing, where it's decreasing then increasing, to see if I can figure out where my minimum and maximums are. So what I'm going to do is I'm going to go ahead and take the derivative of this function, right? So 2/3 x squared minus 4, 2/3 minus 1 is -1/3, and then times the derivative of the inside is 2x. All right, so I'm going to make this look a little bit nicer, and I'm going to say, so I'll multiply the 2x to the numerator, so that's 4x. 3 stays on the bottom, then this goes down to the bottom because it's a negative exponent. So that's like saying x squared minus 4 to the 1/3 power. That's a 3. All right, so now to find the critical points, I get my first derivative and set it equal to 0. So what I can do is I can set the numerator and denominator equal to 0. And if I do that, let's see, if I set my numerator equal to 0, I get x is equal to 0. That one was pretty simple. And then for this one, if I do the denominator equal to 0, I have 3 times x squared minus 4 to the 1/3 is equal to 0. Essentially, I can divide by 3, then cube both sides, and I'm left with x squared minus 4 is equal to 0. So pretty much x is equal to plus or minus 2 here. I mean, you can do all the math, but I guess to save some space, I'll just make it do it quickly like that. Now, this is the way that I like to do these problems. I like to go ahead and make myself a little, my teacher in high school used to call this a wiggle graph. So he likes to make something called a wiggle graph. And with this wiggle graph, what we're going to do is I'm going to put all of my critical values from least to greatest. So it goes from -2, 0, and +2. And then now we're going to kind of observe what's going on here. So naturally, I'm just going to look at my little interval graph here, and I'm going to say, okay, well, these are my intervals. Instead of actually writing out interval and the parentheses and all that, I'm going to pick test points in between these guys, all right? So I'll use a test point over here. I'll try f prime of, a value over here that we can use is like -3. So if I plug in -3 into my derivative function, well, I'm going to have -12 over 3 times 9 minus 4 to the 1/3. Well, that on the bottom is going to be it's going to be a weird number, probably long decimal, but it's just, I know it's going to be positive because 9 minus 4 is +5, and then on the top is negative. So if I have a negative over a positive, my result is just negative. So I'm just going to put a little negative sign there. Then I'm going to pick a test point in between -2 and 0. So if I do f prime of negative, let's do -1. That's the easiest one to use. So if I put a -1 into my derivative function, I have -4 over 3 times, well, -1 squared is 1 minus 4 to the 1/3. So if I take the cube root of something, it'll keep the sign. So in the inside, on the bottom, I'm going to have a negative value. On the top, I'll have a negative. Negative over negative gives us a positive. All right. Then I'm going to go ahead and pick another test point over here. I'll probably choose, let's just do 1. So f prime of 1. If I plugged in 1 into my original function, I'm going to have 4 over 3 times 1 minus 4 to the 1/3. So on the bottom, I'll have a negative. On the top, I obviously have a positive. So that'll make result in a negative value. And then, running out of space, I had more space on my paper, but I'll do f prime. So now I know that this value in this interval, or the slopes in here, are going to be negative. So then if I pick a value over here, I'm going to do f prime of 3. And when I plug in 3 into my derivative function, I have 12 over 3 times 9 minus 4 to the 1/3. Positive over positive gives us a positive value, right? So now what we can do, we can kind of use our wiggle graph to kind of understand what the behavior is. So I know that in this region, if my slope, all of my slopes are going to end up being negative no matter what value I plug into my derivative here. So if my slopes are negative, that's telling me that it's decreasing. If my slopes are positive here, that's telling me that it's decreasing from -2 to 0. From here, it's decreasing. And then from here and above, it's increasing up right there. So that tells me right here that here I'm going to end up with a minimum value. Here I'm going to end up with a maximum value. And then here I'm going to end up with a minimum value. All right. So now, and I don't know, honestly, teachers, from a lot of the different AP exams that I've been looking at, and what a lot of the teachers in the AP community are saying, they're saying that this is no longer acceptable as the answer to a free response question. Now what they're telling us to do is we actually have to sit here and write all of this information out. So you have to say, hey, there is a minimum at this because, and you have to give a full justification. So let's get into it. So first of all, the way you would justify that this is a minimum is you're going to say there is a minimum, a relative minimum at x equals -2 because f prime, was it f? Yeah, f prime of x, because my derivatives change from negative to positive. When you're going from negative to positive, you have a minimum value. So that's what you have to say in writing. Because f of x changes from negative to positive. And you actually have to sit there and write that out for each of these relative extrema. So let's do the next one. The next one is there is a relative max at x equals 0 because f prime of x changes from positive to negative. And then over here, there is a relative minimum, at x equals 2 because f prime of x changes from, I'm getting really sloppy here. I hate writing these out. From negative to positive. It's a pain in the butt, but that's the way they're saying that you have to write it for the AP exam. So I'm probably going to ask a few other teachers to get their opinion about it. But yeah, I meant to change this problem. This is just supposed to find the relative extrema. But I think what I'll do is I'll have you guys do this one on your own. Obviously, I'm going to have the filled in notes posted online. But I kind of want to get into this one right now, because there are different ways of answering the question that says find the intervals of increasing, decreasing versus find the x coordinate of the relative extrema. So let me just kind of go through this problem, and it's just more of the same. Find the derivative, set it equal to 0, figure out your critical points, and then use test points to figure out what the behavior is of the function, whether it's increasing or decreasing, and then decide from there if you have a minimum or maximum. So it's a series of steps, but you have to be able to do that every single time. So first of all, if we want to know increasing, decreasing, or relative extrema, we're going to take the first derivative. So g of x is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So then g prime of x, let's see if I can simplify this a little bit nicer. So that'll be, let's see, that's going to be 2x, 2x squared minus x is going to be x squared. That's going to be minus 4x, and then plus 3. All divided by x minus 2 squared. So then I'm going to make that look even nicer. I'm going to factor it out, and I'm going to say I'm having x minus 3 times x minus 1 over x minus 2 squared. And now what we're going to do, so now that we found the first derivative, we're going to set that equal to 0. Okay? And then we're going to figure out, like if I set my numerator equal to 0, then my critical values will be at positive 1, positive 3. And then here, if I set my denominator equal to 0, I'm going to have another critical value at positive 2. All right? So now what we're going to do is we're going to go ahead and create our wiggle graph. So I have my wiggle graph. I have values of 1, 2, and 3. Okay? So now I'm going to go ahead and plug in test points for this. So a test point that I can plug in from here, I will do f prime of 0. So f prime of 0, I'm going to do, when I plug in 0 into my derivative function to figure out what the behavior of the slope is, I'm going to do 0 minus 3 times 0 minus 1 over 0 minus 2 squared. So this will be negative 3. Negative and negative is positive, over positive is going to be a positive value. So I'm going to put a positive there. Then if I do f prime of, let's pick a value from in between these two. Let's do f prime of 1.5, right? So if I do f prime of 1.5, well, let's see. 1.5 minus 3 is negative 1.5. 1.5 into this would be 0.5 divided by, well, negative 0.5 squared. And then that's negative over positive, so that's going to be a negative value there. Okay? And then what we're going to do, we're going to go ahead and do f prime of, let's do 2.5. So if I plugged in 2.5 into my derivative function, I'm going to have negative 0.5. 2.5 minus 1 is 1.5. Divided by 2.5 minus 2 is 0.5 squared. So here I have a negative over a positive, which is negative again. Interesting. So now I have a negative value there. And then if I plug, I'm just going to plug in 4 for the next point, right, for a value in this interval. So then when I plug in 4 into my derivative function, I'm going to have 4 minus 3 is 1. 4 minus 1 is 3. Divided by 4 minus 2 squared, that'll just be 4. So here I end up with a positive value. So I'm going to put a positive value there. So essentially, this is telling me that I'm increasing from here, decreasing from there, decreasing again, and then I'm increasing from there, right? Which, I mean, this kind of makes sense because if I plugged in 2 into my original function, I would have a vertical asymptote right there. All right, so it's probably having a graph kind of like, you know, like just kind of like maybe going this way and this way. But anyway, so now I can tell that right here, if I'm going from positive to negative, I basically have a maximum value there. Here I don't really have anything, but here I have a minimum value because I'm going from negative to positive. All right. So now to actually answer the question. So we have all of our, we did all of the legwork here, but now we have to interpret all of our results. Again, several years ago, I remember them telling me that this was good enough to answer the question on the AP exam, but now we actually have to justify. So first thing we got to do is it says find the intervals of increasing and decreasing. So let's see. I know that G is increasing from in this region and this region. So I'm going to say G of X increases from negative infinity to 1 and from 3 to infinity since the derivatives are positive, right? So I'm going to say that the way I'm going to say that, I'm going to say since G prime of X is greater than 0. Then I'm also going to say that G of X decreases, right? Because my slopes are negative from this region right here. Decreases from, and remember, we have an asymptote there, so you can't just say from 1 to 3. You have to break it off. From 1 to 2 and from 2 to 3. Since G prime of X is less than 0, because those values are negative, and remember, negative slopes are telling you that it's decreasing. So then, now we got to go ahead and interpret our relative maxes and mins. So we know that there, so where I'm going to say there is a relative max at X equals 1 because G prime of X changes from positive to negative. And then here we're going to say there is a relative min at X equals 3 because G prime of X changes from negative to positive. All right. So for the sake of not making this video longer than it already is, I'm going to go ahead. So I'm going to let you guys try this one on your own, and I want you to at least look at the notes to see how I did it. And then finally, we're going to go ahead and do this last part. All right, so these graphs are a lot more different than what you're used to. First of all, notice how these graphs represent the derivative function, okay? And what they want you to do is find all the critical points and locate all of the relative extrema. Now again, you have to understand, and it's going to be really hard to kind of go back and forth between the original function graph and the derivative graph, all right? But you have to understand that each of these points or each of these values on this graph represents the slope, okay? So when they're saying find all the critical points, I know you're going to be tempted to say, oh, well, that's a critical point because you have a relative minimum. Not necessarily. That would be the case if we're looking at our original graph. Like if we're looking at the original graph of f, yes, that would be a local minimum or a relative minimum or whatever. But when we're thinking about this, we're actually talking about the slopes, or this graph represents all of the different slopes for your original function. So remember how before, I'm trying to find the page from before, but like remember how before, like we would say, there would be a relative minimum at x equals -2 because the derivative changes from negative to positive. We're going to be doing kind of the same thing here. You'll notice that over here, f prime is above the x-axis. So this is telling you that the slopes are positive, right? Or the slopes, or f prime of x is positive. Here, in this whole region right there, say that whole region, the slopes are negative, right? Obviously here the slopes are positive, and here the slopes are negative. So that's pretty much telling. And you'll notice your critical points are going to be wherever it crosses the x-axis. So from here, you're going to be able to determine where you have relative minimums and maximums. So right here, if we're going from positive slopes to negative, and then here we're going to negative slopes. So from positive slopes to negative slopes, that means that we have a relative maximum at that point. Okay? So when we want to go ahead and write write it out for us, here it says there is a relative maximum at x equals -3 because f prime of x changes, because our f prime changes from positive to negative. Changes from positive to negative. Okay? We're going to say there's a relative minimum at this one. So there is a relative minimum at x equals 1 because f prime of x, or our derivative, our slopes, changes from negative to positive. Right? I'll let you go ahead and write the statement for that one. I think you understand what the statements are, and if anything, look at the filled out notes, right? So I'm just going to go ahead and just kind of talk about this one, and again, look at my notes again, the filled in version of the notes if you want to know exactly how I wrote it. But so obviously, where it crosses the x-axis, we know we have critical points right there. But the problem with this one is, you'll see that okay, from here we went from positive to negative, so we have a max there. Here we went from negative to positive, so we have a minimum there. And then from here, we go from positive to positive, right? So if we're going from positive to positive, probably what the graph looks like for this is it's like you have increasing slopes, and then you kind of reach your critical point that has a horizontal tangent line, but then it's probably just going to keep increasing from there. All right? So you don't necessarily have a relative minimum or maximum there, but you do have a horizontal tangent line, okay? So what you would say for that is you would say at x equals 2, there is no relative min or max because f prime of x does not change signs. So either way, that pretty much concludes section 5.2. Like I said at the beginning, if I'm probably going to give you guys a lot more time to work on this problem set because it's just a lot to sink in. There are a lot of different things that you have to keep in mind. But hopefully everything made sense in the video. Sorry for all the interruptions with the bells and all of that. I'm still recording things during classes, but yeah, just go ahead and get started in the problem set. And if you're still confused on anything, just let me know. Or if you have any suggestions about, or if you know, I mean, I don't think any of the ones who took Turnquist class last year, who got 5s or anything like that, are watching these. But if you know the right way of like writing out the format for all of these things, or if there's a more concise way, then just let me know. But I'm pretty sure, like from what I read, this is exactly how the AP exam is going to give you full credit for it. So hopefully it was helpful. I'll let you guys go.